our topic, which is perhaps the central thing that we look for in any CFD exercise that we are going to do, that is how we solve the fluid flow equations. So, we have solved diffusion type of problems, and many times fluid flow is also a diffusion type of problem. For example, if you have negligible acceleration or inertia is not present, it is like a diffusion problem. Many times you are solving a convection diffusion problem where the flow velocity is known. So, that is also not like a real fluid flow problem because flow velocity is known. But the issue comes for this particular topic is where the fluid velocity is not known, and that is what we are going to do or we are going to see. Now, just like any other problem that we have discussed, so we will look into the equations first, that what are our equations. So, we have to remember that fluid flow is not just force balance, it is also mass balance. So, mass conservation, that is the continuity equation, and the force balance or the Newton's second law expressed in terms of the Eulerian variables, that is the so called momentum equation. So, you have the momentum equation. So, let us say you are using a Cartesian coordinate system x1, x2, x3. So, you have the momentum equations in the 3 directions. So, what we are going to see is that how those momentum equations will look like. It is not necessary to expand the momentum equations for solving all our problems, because we can write that in a compact flux form, but sometimes it is not a bad idea to expand, because you will then get a full feel of what are there in the equations. So, you have I equal to 1, I equal to 2, similarly I equal to 3. So, now if you look into these equations, so you have 4 such equations, one is the continuity and the 3 momentum. Before attempting the solution, we have to understand that what is that special feature of this that we have to take into account, which perhaps we did not have to care for when we were talking about the diffusion and convection diffusion problems. What is the uniqueness of these systems of equations? Now, usually when you have a set of equations, and this again from our very school level training, we always try to match is number of equations and number of unknowns. If you have multiple equations and you are formulating those equations, at least we see that do we have enough equations, not just any equation but independent equation, not somehow equations are constructed. So, do you have that? So, it is an accounting that we are all trying to do, number of equations, number of unknowns. So, how many equations we have? We have 4 equations, right, the continuity and the 3 momentum equations. So, you have 4 equations. What are your unknowns? When we say unknowns, we have to write it very generally. In some cases that unknown may be known, but generally what are unknown? So, in all cases you have this velocity u1, u2, u3, or in a different name u, v, w, whatever it is, these are unknown. There is a pressure that is unknown, and density also may be unknown in general, right. May be known for some problem, but in general it may also be unknown, right. So, you have 1, 2, 3, 4, 5, you have 4 equations and 5 unknowns, right. So, this is not our accounting. That means with this accounting we are getting something less in terms of our equation. So, we need more equations. So, one of the equations, if density is say not constant, it can vary with what? It can vary with other properties, and if you have a simple compressible pure substance, not changing its phase, then density can be written as function of two other independent intensive thermodynamic properties. This is from basic thermodynamics. So, for example, you can write density as a function of pressure and temperature. The simplest way in which all of us have learned how to write it is ideal gas, P equal to rho RT, right. So, that is this one as a specific example. For other fluids, it is not this P equal to rho RT, but you can use the van der Waals, so many other equations of state are there. So, this is the mathematical form of what is called as equation of state. Okay. Now, see, with every new thing you are bringing in another trouble. So, what is the trouble that you are bringing in? Now, you have temperature. So, one way where you have no more trouble, trouble means what? Needing to solve additional equations, that is computationally trouble, is if T is constant. So, that is an isothermal problem. But if the problem is not isothermal, then you need a governing equation for temperature, and that is your energy equation that we talked about. So, that is how you see the fluid flow and heat transfer are connected when you have this convection. So, in that way, if you have this and the energy equation, that completes this thing, but then you have the description, but that is not all, you have to solve it. So, to solve it, you recognize certain things. Number one, these are coupled partial differential equations, because the solution of one is influencing the other. These are non-linear partial differential equations. Where the non-linearity comes, the left hand side, see that term partial derivative with respect to x1 of say rho u1 into u1, one such. So, that is a non-linear term. So, in fact, all those three terms in the left hand side after the unsteady term, they are all non-linear terms. So, dealing with non-linear equations is a challenge, because linear equations you can use certain properties both for analytical and numerical solution, but non-linearity handling usually will require always iterative method, and that iterative method it will have its sort of vulnerability to convergence. You cannot use something like the Lax equivalence theorem, and you have to do the grid independent study, all those things come up. So, non-linearity, coupled nature. There is another aspect. So, you have in the right hand side a variable, a dependent variable pressure, but you do not have any separate governing equation that is explicitly talking about pressure. So, this is a big problem, handling pressure, that you have pressure in the right hand side in all those three momentum equations, but you do not have a separate governing equation for pressure. Continuity equation is not a separate governing equation for pressure. So, how to go about it? So, your solution of this Navier-Stokes equation is about developing a management to overcome these issues, and that is why it makes a bit more involved as compared to whatever are the foundations that we have learned for the diffusion and the convection diffusion problem. Now, as the numerical thing developed, see, any subject develops with lot of the subject's insight, but not by keeping common sense away. Common sense is the most important thing for learning anything. So, when you see that pressure is creating a trouble, so one way is that you eliminate pressure. So, how you can do it? See, I will just write this in a vector form, this Navier-Stokes equation. So, you have So, what I have done is I have just written it in a vector form, okay, very compact. My objective is not all the terms, but focus on the pressure term. So, how do you get this vector form is very easy. If you have the 3 components, multiply the x component with the unit vector along x, y component with unit vector along y, and z component with unit vector along z, and just add, you will get the vector form. So, focus on this term. So, if you want to eliminate it, you can use a simple vector calculus identity that you have curl of gradient of a scalar function is a null vector. This is a vector identity. So, what you do is you take the curl of both sides. If you take the curl of both sides, then the curl of this curl of gradient of pressure, it becomes a null vector, right. So, you have eliminated pressure, and that means you are now dealing with curl of velocity. So, this becomes an equation where your variable has shifted from velocity to curl of velocity, which is called as vorticity. So, that is the resulting equation is known as vorticity transport equation, and vorticity typically you cannot just deal with vorticity in an isolated manner. Typically vorticity is connected with stream function in a 2-dimensional incompressible flow. So, that is called as stream function vorticity formulation. We will not get into that. I mean, it is always good to learn that, but it has its restricted appeal, because see, for every problem you have to give boundary condition, but vorticity is not your fundamental physical variable, or stream function is not your fundamental physical variable. Your fundamental physical variables are velocity and pressure. So, to give a boundary condition in a physical problem, it is quite intuitive that if you have the physical description of the problem in terms of velocity, pressure, you can write something which is the physical problem. So, these are called as primary variables or primitive variables. The stream function and vorticity are mathematical variables. So, they are derived variables and they are not primitive variables. So, making boundary conditions for them itself can be a problem from a physical system. So, usually we like it to use the primitive variable, but that vorticity, at least what it is doing is it is giving the advantage of eliminating the pressure, but it brings in the trouble of introducing 2 artificial mathematical functions, vorticity and stream function, not really artificial but derived. So, you have to then give a boundary condition on those which is not naturally defined for a physical system. So, this is not a very good approach of solving all types of problem. Maybe for some type of problem you can very easily describe vorticity and stream function for different boundaries, but it is not quite trivial to do for all. So, this approach is very limited, but this is the intuitive approach. Now, intuitive approach is something, sometimes it is funny, like say you have headache. So, if you cut your head, then you will not have headache, right. So, that is the intuitive approach. So, you have pressure is your headache, so you get rid of the pressure term, then there is no problem, right. So, that is we are having this physiology, modeling of physiology. So, the remedy is if you have headache, you cut your head. So, this is modeling and simulation of physiological flow, right. So, now that you cannot do it like that, and so when we have headache, we try to make a remedy by keeping the head. So, we will now see the remedy by keeping the pressure gradient term and see how still we can manage it. So, we have to recognize that the major aspect that we have to deal with is that you do not have a separate governing equation for pressure. So, artificially you have to construct a separate governing equation for pressure, and what you have in your hand is the continuity equation, which is not a governing equation for pressure. So, The trick is develop an algorithm where you convert the continuity equation in a discrete form to make it a governing equation for pressure, and that is the whole ball game that these all fluid flow solvers they are trying to do. So, here what I have done is I have tried to summarize the challenges in or what are the issues in the Navier-Stokes equation. What I have talked about is a summary of this. We may not have as many equations as number of unknowns, the momentum equation is nonlinear, the continuity and momentum equations are coupled, and pressure field is unknown, but there is no explicit governing equation for pressure. And you are having also other challenges which I am not explicitly telling, that you have a say turbulent flow. Now, if you have a turbulent flow, what you have at least got a feel that to solve a physical problem you need a time discretization and space discretization. So, for a turbulent flow you have wide range of time scales and wide range of length scales. So, the resolution has to be really fine, where you are trying to capture the physics from all the way to the large eddy, which is like of the channel size, to the smallest one which is like the molecular dimension. So, it is not straightforward to do, although in principle you may apply the Navier-Stokes equation, but it will go to such a huge computation, then only for a selected class of problems with very high performance computing power available you can do it. That is known as DNS, direct numerical simulation of turbulent flow. So, that is a challenge, but that is numerical and analytical solution for that it is still not there, and that is why out of all the you can say unsolved problems in classical physics, turbulence remains as an unsolved problem. There are statistical ways of dealing with it, but fundamentally it remains as an unsolved problem in physics. So, in that way so that is one. There is another aspect which we will not cover as a part of this course, but very important, that sensitivity of your solution to your input values, maybe boundary condition as an example. So, you are having an experimental measurement. So, you are saying that at the entry of the pipe the fluid is entering with uniform velocity, with velocity as 1 meter per second. So, you are solving a CFD problem like this. Now, where from you get this? Maybe you have got some experimental data from which you have averaged, that is the best thing that you can do, but your experiment will have uncertainty. So, you will have lot of uncertainty in even prescribing your input, and that uncertainty can get into spoiling your output. If not spoiling, it can give a range of possible errors. So, when we are doing experiments, normally if you have experimental data we draw an error bar, that is an upper limit and lower limit. CFD people normally would not give error bar, but it is not correct, because whatever solution you are giving you should also give a feel of what could be the maximum upper and lower bounds. Say you are predicting the value of pressure of blood of a human patient and giving it to a doctor. Now, you have lots of uncertainties, uncertainty in terms of many things. Patients, the boundary conditions may not be well described from some medical investigation you are approximating, the properties of tissues or blood may not be well properly described. So, all these are uncertainties. So, it will compound to an inaccuracy in the solution. So, if you give the doctor not just the solution, but upper and lower bound, then the doctor will have confidence, okay, if it is not the real value, the exact value, at least it will be bounded by this. So, that itself is a different subject altogether, and nowadays it has become very, very important and advanced because of the advancement of data science. So, how data science has enriched and contributed to recent advancements of CFD, towards the end of this course I will give a particular session on that. So, at least what we can recognize is that uncertainty quantification is a very important thing, and there are different ways of doing that. One very popular method is known as polynomial chaos, is a way, a mathematical technique of it is like a sort of a spectral method type. So, where you are trying to understand the uncertainty of your numerical solution. So, all those things are there, that means that it is not at all straightforward that you give a value and you get a solution and you accept it. So, now pressure is one of the things, it is not just giving a challenge in terms of having no equation for pressure and you are trying to sort of manufacture one equation for pressure, but also how to discretize the pressure gradient. So, we are trying to see that what happens, what is the challenge if you want to discretize the pressure gradient. So, pressure gradient is a very simple term like dp dx. So, if you integrate it say from small e to small w, it becomes p small w minus p small e. So, you have, let us say you have small w higher pressure and p and small e lower pressure and fluid is flowing from left to right. So, this is a very important parameter which is the driving force for the fluid flow. Now, again the question comes interpolation. So, interpolation, so how do you do that? So, if you take that central difference scheme, so p at small e is then half of p at capital E and plus capital P, and this motivation for the interpolation is clear that our variables have their values to be solved at the capital or the uppercase grid points. So, you have to transfer the lowercase ones to the uppercase ones. Similarly, p small w. So, if you now find the difference p small w minus p small e, you get this as half of p capital W minus p capital E. So, nice expression. So, can you tell what is the problem with this? Because expression is very nice, but this is not acceptable. So, when you want to find out a problem, always try to understand the most extreme case. Let us say you have Pw equal to Pe, then that means P capital W equal to P capital E, then your right hand side is 0. So, we are having 3 points which is our focus, capital W, capital P and capital E. Let us say we are plotting pressure versus x. So, let us say we have a situation like this. So, you have P of capital E equal to P of capital W. So, this is one case, but you can also have something like this. Now, this is actually non-zero pressure gradient and this is also non-zero pressure gradient, but this is not able to capture that. So, it can predict something which is physically unrealistic, because somewhere the value of pressure at the point P is nowhere coming into your picture, right. So, you need a remedy for this. So, how do you do? Now, how do you get a remedy for this? Now, you have also similar points similar for velocity, because you have this velocity integration also very similar, like pressure gradient, velocity gradient also the same. So, nowhere the value at capital P is influencing your solution. So, as if whatever is the value of capital P, your answer would be same, but it cannot be like that. Your answer should be influenced by the value at capital P, right. So, one of the ways, this is just one of the way in which this remedy was suggested, is you go for something which is called a staggered grid. That means you use different grids for pressure and velocity. So, if you look into this diagram, so you have this, so whatever control volume is constructed there. So, you have, I will show in the next slide, that you have two different control volumes which are considered for the velocity and the pressure calculations, and they are little bit shifted from one another, and that is why the name staggered grid. But just to make you familiar with the nomenclature, if you can still manage to work with the same grid point for pressure and velocity, then that is called as collocated grid. See, the staggered grid had a problem when? The staggered grid had a problem when we are trying to do linear interpolation, but if we are using higher order interpolation functions, then actually it is not necessary, because then it can accommodate the effect of P. So, collocated grid formulation also is quite common, and when these subjects developed, they all developed with the say geometry of these rectangular type of grids. But with the advancement of geometric modeling, now the method can take any different shapes like triangular or any other forms of the control volumes, and they need not be so well structured in a stencil like I comma j. So, that is called as an unstructured grid or unstructured mesh. So, if an unstructured grid, this staggering has no meaning, right. So, then it is better to have calculation at the same point, and that is why collocated grid is used for that. But the staggering is a very important concept, because conceptually it tells that how to overcome this unrealistic thing that comes in the interpolation. So, remember that what we are doing, the staggered grid is one way of just illustrating it, but the overall conceptual foundation of how to derive the equations, that does not depend on whether it is staggered or collocated grid. So, in the staggered grid, the benefit is that you do not have to interpolate the interfacial properties, that was the problem, and so this kind of wavy field you will not get unrealistic, and pressure is going to drive the flow, but staggered grid will mean more bookkeeping. That means you need to have a separate accounting for the pressure grid points and separate accounting for the velocity grid points. So, how do you stagger this? Maybe let us go to the next one. So, if you consider now these diagrams, it will tell you how do you stagger this. So, what you do is you take your momentum equation or velocity in a way that the capital letters are not, or the uppercase ones are not your grid points, the lowercase one are your grid points. So, it is shifted. What you see in the diagram, say in the x direction, for the discretization that we were talking about in the diffusion or the convection diffusion problem, P would be at the center. Now, here small e is at the center and capital P and capital E are at the boundaries. So, why? Because then if you integrate the dp dx, it will be P at capital E minus P at capital P, and you do not have to interpolate it. So, in that way, if you see, you will get in the x direction, y direction and z direction, it is staggered or shifted, and this staggered means it is staggered with respect to velocity calculation. Okay. So, with respect to velocity calculation in the momentum equation, these are staggered. So, your grid points are now the small letters and neighbors are also small letters, and that is how different names are bit change in the name has to be given. Like you need a grid point which is in the right neighbor, but you have already exhausted the nomenclature small e. So, two small e's e like that. Okay. And if you are writing a code, you have to keep in mind that your indices, those I and j, for main and staggered you have to be very careful. Okay. So, once you have this, now even if you did not have the staggered grid, you will get the equation in the same form for the collocated grid, only instead of small letters it will be the main capital letters, that is it. So, now what we will see that how to solve these equations. So, the three momentum equations for u, v and w are this. as I told that because these are non-linear, you require to go for an iterative scheme. So, you start with an initial guess. So, you make an initial guess for pressure P star. So, why? So, if you make an initial guess for pressure, then your equation becomes like any other equation, because pressure was the extra thing which was creating headache. Now, you have assumed something. So, it has become like a pseudo constant. But if you are putting that in your equation, definitely your equation will not be satisfied. So, if you are putting P star and in turn you get the solution U star, V star and W star, these are not the correct answers of U, V, W, because pressure is a guess. So, the resulting velocity is also not correct. Until or unless you are a magician, you have given the correct guess for pressure and it is giving the correct guess for velocity. So, all what it means is that after you solve these 3 equations with that guess pressure, you have 4 different variables which are your not correct variables, P star, U star, V star, W star. So, how they will become the correct P, U, V, W? If you add the correction which you do not know. So, you have your actual P is equal to P star plus the pressure correction P dash. So, you have the concept of pressure correction and velocity correction. So, in an iterative scheme you are having pressure correction and velocity correction to make sure that from your inaccurate value it is going to converge after some iterations to the correct value. So, now the challenge is that how do you estimate these corrections? You do not know. So, to estimate these corrections, see, even if you do not know anything, say you are solving some equations. So, we have exhausted the use of momentum equation, 3 momentum equations we have used. Continuity equation is still in our pocket. So, we have to see that how we can make use of the continuity equation to make an estimation of these corrections, and the entire way in which the algorithm is developed with that objective it is translating into a mathematical form. So, look at this equation. At the top you have, so had your values been correct, the left hand side would be U and right hand side would be P. When it is not correct, left hand side U star and right hand side P star and also U star. So, now you subtract. If you subtract, you just use the definition that U minus U star is U dash and P minus P star is P dash. Now, to that extent you have the first term and the last term quite well described, but this neighboring term is something which is much more complicated. So, what this algorithm tries to do is to make the calculation simplified, it drops the neighboring term. So, then you can argue that suddenly it is dropping, so it is wrong. So, what you have to recognize is that it is just a way of getting into convergence. So, if you did not drop it, it might lead to a maybe technically more correct way of getting into convergence, but once it is converged by some way or the other, the correction has no meaning because it has converged to the correct value. So, correction is 0. So, whether you drop it or not will matter in terms of how you reach convergence, but once you have reached convergence, that is not going to matter, because our solution is once we have reached convergence. So, omitting that is not going to make us any fundamental error in the final solution. So, if we are omitting that, then you have this AE into UE dash is this. So, you can simplify UE dash is equal to capital AE by small ae, which you give a new name d small e into PP dash minus PE dash. So, you substitute that here. So, you have UE equal to UE star, now you are substituting in terms of this one. So, now you have expressions for velocity in terms of pressure, and then if you substitute pressure correction rather, and if you substitute this in the discretized form of the continuity equation, then you will get a discretized equation on the pressure correction, and that is known as pressure correction equation. So, let us then make use of the continuity equation. So, continuity equation we discretize, and remember that we are discretizing it on the basis of the usual grid, not the staggered grid. Why? Because we are interested to get the values of pressure at the usual grid points. So, we should not stagger this one. So, now if you integrate it, you will get very simple integration, like say d dx of rho u into dx, that is d of rho u, that will be rho u e minus rho u w. So, what then we are doing is we are substituting this u, v, w etc. as u star plus something into the difference in pressure correction. So, if you do that, you will get a governing equation for pressure correction, just like any other equation where you have AP into PP dash is the summation of the A of the neighbors into the P dash of the neighbors plus B, same form of linear algebraic equation that we did for maybe even a 2-dimensional heat conduction problem. So, this is a 3-dimensional, so you have east, west, north, south, top and bottom, very general one. So, this is what is the so called pressure correction equation. So, this equation can be solved, and then you can get P star, and then you can starting from P star you can correct P as P equal to P star plus P dash. So, that will become your new P star, not that with one iteration you have converged. So, in that way you keep on updating your P star, you have the guess P star and then you correct it with such iterative scheme, and once you converge you see that your previous P star and after the iteration new P star is almost the same, and then you say it has converged. So, this method is this is the most popular, and this has been one of the most, I would say, impactful contributions of Professor Patankar, and this is known as simple algorithm. I mean it is a very nice name that he gave. Some students find that it is not that simple, but it is an acronym. It is semi implicit method for pressure linked equations. So, pressure linked equation means pressure is linking the velocity. Why semi implicit? It has nothing to do with that time integration implicit and explicit. So, I will tell why it is semi implicit. So, if you go back to the previous slide, maybe yes. So, if you see in the right hand side, that neighboring term is made 0. So, the velocity correction at a point is related to the pressure correction at the neighboring points, but not with the velocity correction of the neighboring points, but it is actually also a function of the velocity correction of the neighboring points. So, that because of this is called a semi implicit. So, it is not really, it is in a way sort of implicitly connecting pressure and velocity, but not fully, because this is just omitted. So, that is why the name semi implicit method for pressure linked equations. So, what is the algorithm? So, you guess the pressure, solve the momentum equation, that means discretize momentum equation to get u star, v star, w star, solve the P dash equation which is from the continuity equation, you correct P, and then also you can calculate the velocity corrections and you correct the velocity field. So, you take the corrected pressure P as the new guess pressure P star. So, your new P star, and then you repeat it till you get convergence. Okay. So, the Ansys that you are going to use for your calculations, it uses some variant of this simple algorithm, because over a period of time different variants of this algorithm have come, like simplex, simpler, so many other variants are there, but this is the foundation. So, if you understand this, you will recognize that how the velocity and pressure are coupled in a set of equations where you do not have a separate governing equation for pressure, and you are somehow manufacturing it by using the continuity equation. That is the essential learning that you get. So, I have put a few review questions So, let us say you have a one dimensional problem, the momentum equations are like this. So, as if someone has discretized for you and this is your momentum equation. So, you can see that u at the point B is a function of the difference in pressure between 1 and 2, just like your capital P and capital E, and u at the point C, and the boundary condition that u at A is 15. Obtain the values of P1 and P2 following the simple calculation procedure. So, I will just show you how it is done. Again, the whole idea is to get a feel of the method. So, what you now have to do is you have to make a control volume for, see, this control volume is for constructing the pressure correction equation, because your discretized momentum equation is already given to you, possibly using the staggered grid formulation. So, you do not have to do it again, this is given as a part of your problem, but pressure correction is the only thing that you have to formulate. So, we are integrating the continuity, one dimensional continuity is du dx equal to 0, rho is constant. So, continuity equation is u small e equal to u small w. So, in that way, for the grid point 1, if you get back to the diagram in the previous slide, so that means ua equal to ub, right, because its neighbors are A and B. So, the first set of equation for grid point 1, you have the continuity ua equal to ub. Now, you substitute your momentum equation there, so in terms of pressure correction. So, you have ua equal to 5 into 2.5 into P1 dash minus P2 dash. So, and your boundary condition is given, what is the value of ua, you substitute that. So, you will get a equation for P1 dash minus P2 dash. For the grid point 2, you have ub equal to uc, you substitute that, and see, you have ua equal to ub equal to uc, this is physical, that means you have a one dimensional problem, steady state, all points are having the same velocity. So, that is what even the numerical thing is talking about that. So, if you substitute that, you have this star, say I have just marked these two equations as star and double star. So, both of these are giving 15 equal to 5 plus 2.5 into P1 dash minus P2 dash. So, this is where, if this is given in the exam, I have given quite a few times, the CFD course I have taught for many times during my early career, and this problem I used to give sometimes with some change in value, etc. So, this is where most students get stuck. So, I want to solve P1 dash and P2 dash, but I have effectively only one equation, right. So, now you have to keep in mind, and this is a very important concept, that pressure is relative in nature and not absolute. See, even like from your basic idea of fluid statics, we say that pressure at a point is h rho g, school level thing, say you have water and a depth h. So, what does it mean? It means that if you are taking your reference atmospheric level as 0, then with respect to that, if you go to the h level, it is h rho g. So, pressure absolute value is not important for you, and the reason is that in the momentum equation you have dp dx, not p. So, that is delta p by delta x. So, your delta p matters, and you can have many values of delta p for which, or rather many values of p for which you have same delta p. So, say you may have P1 some value, P2 some other value, but still P1 minus P2 all the same. So, there is not a unique solution. So, the trick is that one of these you have to choose as a reference and calculate everything else with respect to that by recognizing the relative nature of pressure. So, let P1 prime equal to 0. So, if you take P1 prime equal to 0, you will get P2 prime equal to minus 4, and then you correct the pressure, and then you can correct the velocity. Here in one step the solution is converged, but this is not magic. There is a reason why in one step it is converged. You think about it, and this is This is like a special very simplified problem, but it is guaranteed whatever you take as your guess in one step it will converge. Sometimes people talk about magic maths, right. They say guess a number, multiply by 10, then they do this and then tell what is there in your mind, then the person will tell this. It is simply an identity that the person is calculating in mind and the final answer will be the same. So it looks, any magic is not a magic. So this is also not a magic, you take any guess, your solution will be the same in one step. Think about it and maybe we will discuss at some point of time. Let us take another problem. So in a one dimensional problem, now you have this one. So just we have added one more grid point and given the boundary condition as one as velocity and another as pressure. So this is just to give you an idea of how to treat a pressure boundary condition. So what you have to do is to write the continuity equation and starting with guess values of P1 and P2, that is P1 star and P2 star, use the simple algorithm to get the result. So I will of course ask you to do it by yourself, but I am just giving you an outline. So you, as I told that you can just take an assumption of the pressure correction. So you assume P1 dash and P2 dash equal to 0 and then from that you can get the U star values and see the continuity equation, and again this is like U small w equal to U small e. One dimensional steady state continuity will be like that only. So you now substitute in place of U small e and U small w the expressions in terms of U star and P dash, and then you get your pressure correction equation. So that will give the final P1 dash equal to P2 dash plus 4. So this is what you get for the point 1. Similarly for the point 2 you will get 4 P2 dash plus P1 dash equal to 30. So if you now solve these two, you will get P1 dash and P2 dash and you can correct that P1 and P2. So again it appears that with one iteration it has converged. So now can you say that in the previous one we were finding that you had one equation with two unknowns, but here you have the equation and unknowns the same. So the only difference is that here you have given a pressure boundary condition. So your relative nature of pressure is set up by the value of that boundary condition. In the previous it was a velocity boundary condition, so you had to set it up with your reference. So that is the only difference, but otherwise the calculation scheme is the same. Now this is a two dimensional problem. So in the two dimensional problem you are given UW, VS, PN, PE etc. Like staggered grid means you are dealing with small letters for velocity and capital letters for pressure. So you are putting that and the control volume in this diagram, of course delta x and delta y are shown schematically different, but for your calculation you can take these as same. Use the simple algorithm to obtain this whatever are not given, that is U small e, V small n and P at capital P. Other points the values are given. So these are actually artificial problems, but these are given to create a concept in you. So you can take, so wherever this pressure correction is not given you can assume something. So what you can do is you can assume the value of pressure. So once you assume the value of pressure you will get a value of velocity, because your equation is of the form U star is a function of P star. So put a value of P star and you will get a value U star. If P star is not correct, U star is also not correct. That is the central philosophy, very simple. From my learning of not just this subject but many subjects, what I would always urge you to do, that try to think simple. make your mind simple. If your mind for learning a scientific subject is like a child, you will learn the best. So, do not over complicate a thing which is actually not complicated. So, once you now you have the continuity equation, you integrate it over the main control volume, and in that you put all those expressions, and once you put all those expressions you will see there is only one unknown, which is the pressure correction at P. So, that is solved, and then you will get the expressions for the new velocity and new pressure, and here also by some way maybe in one iteration it has converged. So, this gives you the overall idea that what we are doing, we are guessing pressure, we are putting that guessed pressure into the discretized momentum equation to get a velocity, because your guess is not in general correct, that is also not in general correct. So, that velocity you substitute, or once you have that velocity, then you can substitute that velocity in the discretized continuity equation, and because your pressure is not correct, you write that pressure as P star plus P dash, where that P dash you can get from the discretized momentum equation. So, all the velocities are expressed in terms of the P dash, and that expression is substituted in the discretized continuity equation, and that will give you a pressure correction equation which you are solving. That is the whole idea for this. So, with this we end up here for the this fluid flow equation. We will continue with the next topics, and next what we have is, I think, introduction to this how to work with Ansys, and we will move forward with that.